Why are airfoil impellers often selected for high-efficiency centrifugal fans? Near the intended duty point, a well-designed airfoil blade can reduce aerodynamic loss. But an airfoil label never guarantees the highest efficiency at every flow rate, speed, or installation. The first difference is the blade section. A flat plate has almost no thickness, while a basic curved plate mainly redirects the flow. An airfoil adds a rounded leading edge, controlled thickness, camber, and a thin trailing edge. Together, those features manage acceleration and diffusion through the rotating passage. The next question is incidence. How does the relative inlet flow meet the leading edge? When the inlet velocity triangle matches the blade angle, the flow approaches the rounded nose smoothly. A mismatch creates positive or negative incidence, concentrating loss before the air has crossed most of the blade. Across the section, the pressure surface carries higher static pressure and the suction surface carries lower pressure. That pressure difference creates aerodynamic loading and turns the relative flow. The engineering goal is not maximum loading at one spot, but the required turning with controlled pressure recovery and limited mixing loss. Now zoom into the boundary layer, the thin region of slower air touching the blade. Near the design condition, a suitable pressure gradient can keep it attached over much of the surface. An attached layer reaches the trailing edge with a comparatively narrow wake, leaving less kinetic energy to be dissipated downstream. Move away from the intended range and the picture changes. Incidence rises, an adverse pressure gradient can overpower the low momentum boundary layer, and separation appears. The wake widens, turbulence can increase, and broadband noise may rise. These are conditional mechanisms, not guaranteed acoustic values. A fair shape comparison must hold the inlet condition, diameter, speed, flow coefficient, pressure target, Reynolds number range, clearance, and surface quality as consistently as possible. Under comparable conditions, a shaped airfoil can guide the flow more gradually than a flat or simple curved plate. This animation explains the mechanism. It is not measured CFD or a fabricated efficiency result. For model-specific evidence, this Longwell RLM250 page plots pressure, efficiency, power, speed, tip speed, and sound power information for its declared test and installation conditions. Mark the required duty point on the exact model curve. Do not transfer an RLM250 result to another diameter, motor, inlet, or fan family. The EC250 footage is genuine Longwell manufacturing imagery. It verifies visible backward curved geometry, assembly, and finish. It does not reveal a hidden blade cross-section and does not prove an efficiency or noise number. Real footage and engineering animation have different jobs, and the video keeps that boundary visible. Efficiency belongs to the complete fan and operating point. Inlet distortion, hub and shroud geometry, tip clearance, roughness, diffuser or volute design, motor and drive losses, air density, and system resistance can all change the result. Even an excellent airfoil impeller can perform poorly when the system forces it far from its intended region. For a design review, request the airflow pressure curve, efficiency curve, input power, rotational speed, acoustic data, test standard, density condition, installation category, and production tolerance. Then overlay the required duty point and expected operating range. Ask what happens at part load, not only at one catalog peak. The practical conclusion is simple. Airfoil geometry can create a strong efficiency advantage when its section, incidence, complete fan, and tested operating region all match the system. Choose from verified curves and stated boundaries, not from the blade name alone.